For this second installment of simple harmonic motion, we are going to determine how to come up with the expression we have for the period of a pendulum. And to do that, we are, just like we did with the mass and spring system, going to look at how the forces relate to the wave motion of the pendulum. And so in these three views of the pendulum on the left, we've got the pendulum at equilibrium, and then the next two views show the pendulum at an extreme of 12 degrees to the left or 12 degrees to the right from its equilibrium position. At both of those two orientations, the pendulum is experiencing an acceleration that you will notice points back down at an angle towards equilibrium, because remember, the end of the pendulum is following a circular path, which creates a bit of a problem, because then when we try to identify the forces, tension is pulling the end of the pendulum towards the center of the circular path that the end of the pendulum follows, which is also the fixed point. But the problem with that is it doesn't ever point in the direction of the acceleration. But then if we look at the other force present, gravity, it also doesn't actually point in the direction of the acceleration. So these linear quantities, unfortunately, don't seem to be fitting with the wave equation that we use to find the pendulum, the period of the mass spring system, and should still describe the motion of the pendulum. But if we switch up and instead look for torques, then what we find is that the pendulum has an angular displacement that is going to pull it away from equilibrium, which happens to be the exact angle that you started at, and then it decreases and flips to the other side as the pendulum swings. And then as the pendulum is rotating about its center, it's going to experience an angular acceleration that pulls it back towards the equilibrium position. And that pair of vectors happen to point in opposite directions, which does indeed satisfy the wave equation. Just notice that now the wave equation is in an angular form. Well, if the wave equation is in an angular form, we need to identify a force that produces a torque, the angular analog to force, to produce that angular acceleration. Tension's not the one. It's going to turn out to be gravity. Now, while it may seem counterintuitive that gravity is producing the torque, since gravity is pulling down all the time and never changing, it is the angle that the pendulum makes the equilibrium that creates the torque effect of gravity. And that torque will happen to point in the same direction as the angular acceleration, no matter where you look at the orientation of the pendulum. So it is the torque of gravity that does indeed create the angular acceleration that drives the simple harmonic motion of the pendulum. So how much is that torque? The general form for torque is that we should be multiplying r times f times sine theta. The r is the distance from the point of rotation, which is the fixed point of the pendulum, to where the force acts, which is the end of the pendulum. The force is gravity. The theta should be the angle between r and f, and as you can see, that theta happens to match up to the same theta as the angular displacement of the pendulum. Notice that there's a negative because the direction that we had the torque pointing before points opposite to the direction of the angular displacement. And so to show that those two vectors are opposite, we stick a negative in there. Now, just to finish cleaning things up, the r also happens to be the length of the pendulum, so we can make that substitution. And the magnitude of the force depends on the mass of the pendulum and the gravitational field strength, so that we end up with the torque of gravity being negative Lmg sine theta. So let's piece all this together to get the period of the pendulum. So again, anytime you've got some kind of simple harmonic motion, you have to satisfy the wave equation, but because the pendulum is better described by angular quantities, we substitute alpha for a and theta for x. And now, in order to get an expression for alpha, we apply Newton's second law in an angular form that says that the angular acceleration driving the pendulum's motion is caused by the torque due to gravity. Remember that there is that rotational inertia term that pieces those two together. If we piece these equations together, we end up with the relationship shown here. And now we just need to come up with an expression for the torque, which we already have is negative Lmg sine theta. And for the rotational inertia, remember, since all the mass of the pendulum is at the end, that's basically like a hoop. And so the rotational inertia for the pendulum is ml squared. And if we piece those together to look just like the other side, we now have equations that can be substituted across, and we can piece together all of these random quantities associated with the orientation, with the rotation and oscillation of the pendulum, and then we can start canceling things. The negatives go, and then we can cancel the masses, which agrees with our findings that the mass of the pendulum doesn't actually affect its oscillation. And then we can cancel one of the lengths, which agrees with our findings that the L does affect it. Now, we've said before that the theta doesn't actually seem to affect it, but we had to put a caveat on that. We had to assume what was called the small angle approximation. This equivalency is actually not entirely true. For the most part, theta is actually less. Sine of theta is actually less than theta. But for small values of theta, they are roughly equal, and those values are something less than about 0.21 radians, or about 12 degrees. So as long as we keep our angle small, we can make this equivalency. Substitute away the theta, and now we have this expression, which allows us to show that the theta does indeed cancel, and we can finish piecing this together to show that the square of the angular frequency is g over L. And then if we piece that together with the definition for the angular frequency, get everything to line up and put the omegas together, then we can show that the square root of g over L should be 2 pi over the period, rearrange those quantities, and we have the expression for the period of a pendulum. And it only depends on the length of the pendulum, and it is inversely proportional to the gravitational field strength of that pendulum. And now I have a challenge for you. This is a smoke tree. I want to know how high this branch is. I don't have a meter stick, just a swing and a child.